Okay. Hello, friends. So let's start the last lecture in semiconductors, and we'll start with cutoff region. Now, what we have already discussed is the active zone, which is here, in which we discussed that IC is dependent on IB. As we keep increasing IB here, then IC gets increased, independent of VCE, IC. And then we also discuss saturation region. So in saturation region, we know that the IC is governed by VCE, and the base collector PN junction becomes forward biased. Alright. So now we come to the third case, in which both the junctions are reverse biased, which means this PN junction, which is emitter based PN junction, is also reverse biased, and this collector based PN junction is also reverse biased. So reverse biasing a PNP emitter based PN junction means connecting this base N side to the positive lead of the battery, and then here like that. so the transistor action is not there, isn't it? Because transistor action happens when this electric field drives lots and lots of holes here, but then the electric field of the battery here, this VBB, this is actually opposite, isn't it? So not at all forward bias. So we know that this is also reverse bias, so a reverse extremely small current will flow here, and this will also be an extremely small reverse current. So nothing happens, nothing much. Both the currents are nearly identical, maybe nearly equal to 0, and IC tends to 0, IB tends to IE tends to 0, and we say that the transistor is off. Like when the switch is off, we say that no current flows. Similarly, we say that the transistor is almost off, negligible currents of the order of 1 to 5 microampere, negligible there. So that's what is the cutoff region. So now we can say that there are 4 cases here of the transistor, which is for the, let's say this is a base emitter PN junction, and this is a collector base PN junction, and the possibilities are, this is forward biased and this is reverse biased, or we can say both are forward biased, or both are reverse biased, or this is forward bias and this is reverse bias. So now we know that this forward bias, reverse bias means active state, both forward bias means saturation, both reverse bias means transistor is in the cutoff stage, nothing happens, both are reverse bias, so not much current flows, negligible current. And then when the collector base PN junction becomes forward bias and base emitter PN junction becomes reverse bias, now in this case the role of collector is taken by emitter and the role of emitter is taken by collector. That means now, because of this being forward bias, the holes are transferred from this PN junction, the collector, into the emitter, so roles are reversed. So that is generally not considered here. I mean, the transistor is not operated in this region. So now we are all set with all 4 kinds of possibilities here regarding the biasing. Moving on to transistor as an amplifier here. Alright, let me just straighten it. We know that in active state, the IC equal to beta IB, or we can say delta IC equal to beta delta IB. And we know that during the transistor operation, beta doesn't change. So this beta is of the order of 100, normally 100 to 100, and this we know that there is a relationship between beta and alpha also, you may remember. So a change in x ampere of IB, if delta IB is x ampere, will change 100x ampere in IC, obviously, because of this beta. So this is what is called as the current gain. We'll discuss about it. So let's say we have a very small sinusoidal voltage input and we want to amplify it. So we have already discussed about the amplifiers previously, if you remember the previous lectures in detail, isn't it? So generally the input voltage, which is sinusoidal in nature, is like this, sinusoidal voltage, and when this needs to be amplified, we need a larger amplitude, isn't it? So all those things are already discussed in the previous lecture. You can just go through it if you want. Alright. Now, so whatever voltage is applied here, I mean needs to be amplified here, we can put it here across this base emitter PN junction. But then there is a problem. What is that? See, when this base emitter PN junction is forward biased during the half cycle of this input voltage, which is this, then no problem, this PN junction is forward biased, and since this is forward biased and this is anyway reverse biased with the help of this VCC, there will be a huge amount of current gain here, and because of current gain we'll get voltage gain also, so not a problem. But what happens in this remaining half? In this remaining half, when this base emitter PN junction, this becomes reverse bias because of the negative value of this voltage here, this becomes reverse bias, and this is anyway reverse bias, so the transistor is in the cutoff region, and when the transistor is in cutoff region, no current flows, and then nothing happens basically. So the input voltage is 0, the input voltage is negative, the output voltage is whatever, that like current is not there, so ICR is 0 because of IC being 0. So basically we don't get any voltage or something like that. So there is a problem here, isn't it? So how are we going to rectify it? The same problem was discussed during the amplifiers chapter also. So let me just check where it is. Hold on a second. So here is this thing, and this is out of phase as we discussed in the previous lectures. This is the problem here. So we are going to get a voltage here, but then in the negative bias transistor doesn't work like this. So what we discussed at that time is that we are going to use this DC biasing. The same thing we are going to do here in case of transistor also. So DC biasing is done. So DC biasing is done means apart from this sinusoidally fluctuating input voltage, we are going to connect a battery also. Alright, so here is the thing. So this is VBB and this is VI. So we can say that the total input voltage will be this VBB plus this sinusoidally varying input signal, which needs to be amplified. Remember that we want this to be amplified, and we are using this just to help this VI, so that this VI doesn't make this base emitter PN junction reverse biased. Alright, so VBB and VI connected across this emitter base PN junction. So this is what is the input circuit here. Care should be taken that the entire total input voltage, which is from here to here, this is what is the total EMF source we have applied, a battery and an input signal. This total voltage should always be positive, and for that this VBB should be greater than VI, because the max value of this is going to be VBB plus VI, but the minimum value is going to be VBB minus VI, because this is going from plus VI naught to minus VI naught kind of thing, which I have explained here. See, if we assume this VI to be equal to VIO sin omega t, then when it is positive, not a problem, both gets added up and we get a total of VBB plus VIO. But when this becomes negative, then the total input voltage becomes negative, and the maximum negative when it is, the entire voltage will be minimum, so that the minimum input voltage will be VBB minus VIO. So this is how it varies. So this is VBB, and it goes up by VIO, it goes down by VIO. VIO is the amplitude of the input sinusoidally fluctuating input signal, which we want to amplify. So that is what is the input side here. So this is a very basic simple connect electricity thing. We have applied Kirchhoff's voltage law in this input side, and here we have this RB, VBB, IB. So let's apply. So what we are going to do is we are going to start from this base terminal, and we are going up till the emitter terminal. So as we go, since this is a PNP transistor, so the current will be going like this. This is the base current IB. So as we go from this like this, we get minus IBRB. We are starting from the potential of the base, so this is the starting potential. Then we go to, then the total decrease in potential is IBRB, so net potential becomes whatever potential we started with minus the drop, and then there is a addition of the voltage because we go across the EMF source, which is VBB plus VI. This VI again is input voltage, so it can contribute or it can oppose, and then we go to, or we come to VE. So this is what is a simple Kirchhoff's law. So as we take this from here to here, we get VE minus VB. VE minus VB is, we know that the base emitter PN junction potential difference, which we can call as VEB. VEB here is, as you know, VE minus VB, the difference between the potentials of the p-type emitter and the n-type base. Alright, so this is the total input voltage. The total input voltage is written as WIN. So remember, this WIN is different from WI. WI is the input sinusoidally fluctuating input signal which we want to amplify, together with this DC biasing voltage together make up the entire input voltage. So this entire input voltage minus IBRB is VEB. Alright, so this is what is written over here, the total input voltage. Now the total input voltage keeps changing because of Vi. Now if these fluctuations were not there, these fluctuations are not there, the total input voltage will be the VBB only. So that's what is written here, the input voltage without fluctuation is VBB. So we can check what is the change in the input voltage because of the fluctuations. So we are saying that the DC biasing voltage is the normal voltage, and on top of that we are imposing, or we can say superposing, the sinusoidally varying input function, input voltage. So what is the change possible? So this is the normal value without any fluctuation, and then when we add fluctuations, which is the Vi, which is VIO sin omega t, then whatever we are adding is going to be the change, isn't it? So the change will be when it is added up minus when it was not added, which is basically Vi. Now, so this change in the input voltage over and above this VBB is equal to this Vi. Now this Vi keeps changing, isn't it, sinusoidally as the time progresses. So because of the change in input voltage, the base current will change obviously. If we change the total input voltage across the base emitter PN junction, the input current is supposed to change, isn't it? And the voltage across the base emitter PN junction also increases. So when we increase this input voltage, for example, then this will also increase, isn't it? So this we have got from the Cutoff's law, that the total input voltage here, if you remember this, I hope you are able to see this. This is the total input voltage VIN, and this VIN, if we transfer this to this side, then we get VEB plus IBRB. So input voltage VEB plus IBRB, that's what is written over here. So when this total input voltage changes, assuming its normal value to be simply the DC biasing voltage, so what is the change here? This delta VIN, and as the input voltage change, it may cause a change in the emitter base PN junction potential difference, and obviously it will bring about a change in the base current. The larger you forward bias the base emitter PN junction, the larger is going to be the IB. So IB will increase as we keep increasing the input voltage. Similarly, this input voltage can decrease also, because for half cycle this VIN is going to be VI is going to be negative. Okay, alright. Now if you remember, previously we discussed the input resistance. Input resistance is the change in the base emitter PN junction potential difference required to create a unit change in the base current. So that is what is here written. This is already discussed previously in the input characteristics, that Ri, the input resistance, is equal to this. So we can say that the change in the emitter base PN junction potential difference is equal to delta IB into RB. So if we substitute this delta VBE here as IB RB, so we get delta IB also and delta IB. So VI, see why we are writing this as VI when it was delta VIN? Because the change in the total input voltage is the input signal, isn't it, over and above the DC biasing voltage. DC biasing voltage is the normal input voltage, and when we add the input signal, the total input voltage becomes VBB plus V sinusoidally varying input function, this, and this is the final value. And what is the initial value without any input voltage? This VBB only, the DC biasing. So what is the change? So the change in the total input voltage is input voltage with sinusoidally varying input voltage, input signal, minus the DC biasing that was there previously. So that is VI. So this VI is VIO sin omega t. This, that is equal to delta IBRB plus delta IBRB Ri. So this RI and RB are taken common, sent on to the other side. So we get the change in the base current due to the introduction of VI in series with VBB. It's a very simple thing. So this is what is the sinusoidal fluctuations in IB. See, remember that we are interested only in the fluctuations because we are not interested in DC biasing. All those concepts are already covered in the amplifier thing. Now, because of the change in the base current, the change in collector current will also happen. So we do define the current gain as this. This is considered as output current. So delta AC means change in output current. So current gain is defined as the change in the output current per unit change in input current. That means when we change the input current by some X amount, how much does the output current change? That's what is called as the current gain, represented by AI. So current gain is equal to AI, which is equal to beta, isn't it? Beta is roughly of the order of 100. Moving on. Now we have drawn the output side also apart from the input side. So we know that input side consists of RB, the VI, and this is VBB, and together this is total V input IN